Hi, and welcome to this week's presentation as part of IOLITE's Python for LA-ICP-MS course. In this week, we'll be discussing database interactions and how to access data in the database via IOLITE's Python API. In today's presentation, we'll be looking at how to get data from the database so that we can perform calculations on data from the database and potentially also add new data to the database. Using these simple concepts, we'll use our database to gather insights into our long-term trends within our database. There is some background knowledge required for this presentation though. Firstly, it's assumed that you're at least familiar with SQL commands. If you're not, I suggest that you read the Python and Databases chapter in the Py4E textbook, and I'd also recommend the W3 School's free SQL tutorials. I'll put some links in the notes for those. It's also expected that you're familiar with IOLITE's database feature in general. So that means at least having watched the webinar about the database. There is an example dataset for this presentation that you can use to follow along with the examples. That dataset is called python_db_example.db, and there'll be a link to that in the notes that go with this presentation. Basically, this example database is a synthetic dataset where I've just replicated the draw.io4 session file and replicated it about 40 times so that we'd have some spread in time values, so that later on when we look at an example of a dashboard, we'd have some data spread out over a few months. All of the data are basically just replicated except for this final 206.238 channel, which I added some noise to so that it wouldn't look like it was just the same values over and over again. I'll put up the code that I used to do this because it can be interesting to see how you can directly interact with SQL databases in Python as well. But you can basically see that I brought in the original database and then I calculated some results, some statistics from those for the Plišović and Tomorrow values, and then later on I calculated some raw data using this random Gaussian distribution using the mean and the 2SE, and then putting it back into the database here. I also created a couple of new channels for a couple of new columns for the database, and this was work type and analysis type, and they're just randomly assigned based on some weighting. So this, as I mentioned, the work type and the analysis type, they're basically trying to capture who the customer was, so whether it was an academic customer, a government, or an industry partner. And the analysis type was supposed to represent whether or not this was a geochronology experiment, or if it was a Hafnium isotopes experiment, or a trace elements experiment. Of course, normally you would assign these during the session, but because this is just the one geochronology data set that's being replicated, I've just randomly assigned what they are, just so that we had some variation. When you first go to the example database, you'll see that the columns are all out of order. And I think that this is because when I randomized things, I messed up the column order. But we can fix that by going to filter columns, and we'll just show the session name, the group type, the group name, the name of the selection, the start time. We'll also put in this analysis type and work type columns as well. We'll also show this total bean column as well, just so that we can see it. Now let's look at how to access the database via Python. Now, I should point out that in the last few weeks, we've been talking about writing modules, like an importer module or a DRS module. In this case, we're not really doing that. We're accessing the data via the DB object, which is available in IOLITE's Python workspace, IOLITE's Python console, any Python code actions that are in processing templates, and the scripts that are run in the database view. So those that are run when you click on this button down here. Let's look at some examples of that now. So if I I have my database open, and if I open the Python console and type in db.active_file, it will actually print out the path to the currently open database. And that just shows that by using this DB keyword, we can access this database. Similarly, if I go to the Python workspace and just in an unsaved script, type in print db.activeFile and run that, you can see that it will be evaluated as well, and it has access to the database. You can see over here we have this DB keyword showing that it's the database Python interface. Also, if you go to templates and click and add a run Python code action, and we'll call this run script, and you can add code into this action here, or you can write a script that can run. But normally this would be part of a larger processing template, of course. But just to show that you can access the database via this as well, we could type in db.activeFile, and we'll actually print the result of that. And so now, if I just clear the Python console, because this print will print to the Python console, when I click run, you can see that it has printed out this. So the database is available in the processing templates as well. And finally, in the database view, there is this run script button down the bottom here. If you click and hold on it, it will show you the built-in or scripts that come with IOLITE. And if you click this new button, it'll prompt you to create a new script. So we can just call this test script. And you can use one of the existing scripts as a template. You can always go back and remove any of that if you need to. If I click OK, you can see that we now have a test script in our list here. If I was to click on this Open User Scripts folder, it takes us to this folder here, which is normally in your Documents /IOLITE/scripts/database folder. And you can see that there's now this test script, and you can open that in your favorite script editing software and work on it there as well. But now it's in this menu so that you can rerun it anytime you want. So we've already seen this db.activeFile. You can use this to check to make sure that a database is open. If there is no database open, it will raise a runtime error. Now let's look at getting data from the database. The first we'll look at is db.column. This function, in its simplest form, just takes the name of the column that you want. Let's have a look at an example now. So I've just zoomed in on my Python console so that hopefully you can see it a little bit better. But let's look at that db.column function. So in its simplest form, we can type in db.column, and we just put in the name of our column that we want to return. So we could type in here total beam, and it would return an array containing the values of this column. We can assign that to a variable. So let's assign that to a variable called col. And now col is associated with that array. We can also look at the length of that, and you can see that we now have all 14,233 values from our database here in this array. But there's some other parameters to this db.column function. The first that we've seen was the column name, which is just a string. But there's also this query mode, which by default is db.all. And there's also this query string, which by default is an empty string. Let's look at what they are now. So the query mode is one of three options. db.all, that will return all the rows for the column requested from the database. Another option is the db.model, and that will return only those that are currently visible in the database view. And the third option is db.specified, and this is where that third parameter, the query string, comes into play. If you type in db.specified, you can then add an SQL statement that will be used to select the rows to be returned. Let's look at some examples of those now. I'm going to return the name column just so that we can see the differences nice and easily. So if I was to put in db.column column, and we're going to return the name column, and we'll use db.all. What we'll see is that we have an array, and because the baseline selections don't have any names, there'll be none for those, but for all the rest it will have the values from here, and that's returning all the values. So we can look at that, at the length of that. And you can see that that has all 14,000 odd values. But if we were to add a filter in our database view, that would change what would happen when we use the db.model. So let's filter our database for all the places where the group name contains the letters PLES. So now we've just selected for Plesvice. So now if we were to type in db.column, and again using name, but this time using db.model, it would just return the values that we can see here. So they're all Plesvice in this case. So that's the difference between using db.all and db.model. But what about db.specified? Well, let's look at an example of that now. So if we were to use db.column and we wanted to return the name column again, and this time we're going to use db.specified, and now we're going to use that query string to specify what rows to return. So we want to return just the rows that have Temora in the name. So we'll say select all from results where name like, and here we have to be a little bit careful about what quotation marks we use. If we use a single quotation mark, you can see that it will finish off, it'll close out this string that we've started making. So we need to use a different quotation mark. In this case, we'll use double quotation marks because we've used a single at the start here. So we'll say like tem, put in another percentage sign as a wildcard, then we'll close that string, and now we'll close our entire query string. Then we'll close the brackets, and you can see that it's now selected all the rows that have tem in the name. So it's selected just those for us. So that's the differences between db.all, which returns all the rows in the database, db.model, that returns the currently visible rows in the database view, and db.specified, where we set the SQL statement string. And as I mentioned, you just need to take care between your opening and closing quotation marks. In general, in Python, we tend to use single quotation marks for opening and closing strings. But then if you're looking for a particular value and you need to enclose that in quotation marks, I'd use double quotation marks in that case. And just a quick note that sometimes if you're converting your column array to a NumPy array, which is quite common, something that you quite commonly want to do, sometimes it can be a good idea to set the data type, and you just do that by returning the array values and then passing this dtype parameter mp.float64, and that will make sure that the array is treated as a numeric array instead of some other type. So that's getting individual columns from the database, but sometimes you want to return the entire data frame, and you can do that by using this db.dataframe. That will return all the columns from the database, and this only takes two parameters, the query mode and the query. And just like we saw before, this is db.all or db.model or db.specified, and if it's db.specified, you can include the query string there as well. So now let's look at adding information to the database. In the database webinar, we looked at how to export selection labels from an experiment from a particular group and put that into an Excel spreadsheet. Then you can look at that spreadsheet and add extra properties to that. So here is an example where we've exported all of our selection labels, and then we've updated for each selection what its IGSN was, what field trip it was collected on, and what publication it's associated with. And this is all done in a spreadsheet, so it's nice and easy to type in. And then after you've done that, you can then import that spreadsheet, completed spreadsheet, back into the experiment, and it'll assign those properties, those columns, as properties to the selections. That's normally done all within the session before you import it into the database. But we can also add information to the database directly using the Python API. And we can do that via this db.appendColumn function. It takes the name for the new column, an array of values to be updated, and a query mode and a query string, just like we've seen before. So an example of that would be where you're adding a new column called test column, and you have an array of values you want to assign to that column, and we're telling it to assign them wherever this SQL statement is true. So let's look at an example of that now. So let's say that I wanted to create a new column that had a particular value wherever one of the other columns had a particular value. Now I could do this off any of the columns, it could be numeric or it could be text data, but in this case I'm just going to do it based off one of the text columns, so it's nice and easy to see, because with numeric data it could come from anything. So first off, what I'm going to do is I'm going to create an array that has the same length as the number of selections that meet my criteria. So I'm going to create an array that is the values from the group name. So I'm going to say names equals db.column. We'll get the group name. It doesn't matter which one. Group name column db.specified, because I'm selecting based on the group name. And we say select all from results where group name like, I just use like so that I don't have to be exact, like Liz, and then we'll close that out. And so now we have an array of names. It's all Plezovice, that's what we'd hope to see. And we can get the length of that as well. So that's how many entries we'll want to make in our new array. That's how long it will need to be. So I'm just going to duplicate that and say it's equal to some other text value. So I'll do that by, let's say new vals equals, we're just going to do list. So it's just going to be equal to, I know, this is Ples for X in new vals. Oops, sorry, that should be names, our existing array. So now new vals is the same length as our names, but it has this text, this random text, or this just a dummy text value that I'm going to put in. And I'm actually going to turn that into a NumPy array. I should have put that into a NumPy array. So we say new vals, I'll just use the same variable name equals np. I'll have to import NumPy first. NumPy as np. We'll say new vals equals NumPy array, and it's going to take that array, new vals, and now that new vals is a NumPy array. So now that we have our array of values that we want to add into the database, we can use this db.appendColumn. We'll give it a name, so we'll just say this is plescol, just for some random name for it. We'll say db.specified, because we're only updating certain rows, and we're going to say, like we've done before, select star from results where group name like ples. Close that out, and I did a typo in there. Oh, I forgot to pass the actual array as well. So I've given the name, but I forgot to give the values, which is our new vals array. So now if we go to our columns, there should be another one now called plescol, and you can see that wherever this group name equals plesavice, that this has updated with a value. So that's one way, and like I mentioned, this is just a very simple contrived example, but it shows that you can create a new column that only has certain values for certain places. And I just did a simple select here, but you could actually make that quite complex. Just some notes about adding information to the database though. At the moment, you can't overwrite a column of the same name. If you try, it won't actually even tell you that there's been an error. It just won't work. Also, you can't, within IOLITE, drop an existing column. You can only create a new column. That's because in SQLite versions less than version 3.35, there was no drop column command. However, now that versions 3.35 are available, they have a drop column command in it. And if you use something like Beekeeper Studio or DB Browser for SQLite, which are both free, you can actually type in this command down here with your database open, alter table, results, drop column, and the name of the column that you want to drop. So you can't do it in IOLITE at this point, but you can use one of these other database programs to drop columns if you need to, if you've made a mistake and you want to get rid of a column. So let's just do a quick review of the long-term uncertainty calculation script that Joe wrote and comes with IOLITE by default. So obviously I'm not going to live code this. I'm just going to show you, go through what's been done here so you can see how it can be used to calculate and add results to your database looking at long-term results. So there is a bit of setup at the start here, some functions that will return lists of channels and uncertainty channels, and also the selection groups. There is this little bit of a longer term thing, which is a queue dialog that has been modified so that it will allow the user to select the channel that you want to calculate the long-term uncertainty for and the associated uncertainty that goes with that, and it also return the group for that as well. So then when the script executes, it presents this dialog, and that's where the user can select those options. And then it will create a data frame. So you can see that it's using this db.column to pull out the values for the value channel, which is just being returned from the dialog up here, and the uncertainty. And it's also only pulling them out for that particular group. So it's using this db.specified and selecting from results where the group name is equal to the group that's been selected. It also kicks out any NaN values, and it will also get rid of any outliers that are greater than 3 SD. It then puts this into this weighted mean function, which is imported from IOLITE helpers. So there's this script IOLITE helpers that has quite a few statistical functions that you can look up that IOLITE uses, and it's just importing the weighted mean from that package. And the weighted mean actually returns a couple of different things. One of those things is the extra uncertainty to be added to it. There's a few other things as well that you can see if you run this script. Then you can see that it is taking the value channel, so whatever the name of the channel that we selected, or the user selected, and it's creating a new channel called that'll have that name appended with long-term 2SE appended to it. And it's then adding in quadrature this external extra sigma, which is this extra part from the weighted mean that's returned. And it's doing this append column with that name and the long-term uncertainty. So I just thought that now that you've seen some of those abilities, that would show how you can use those to do something like calculate long-term uncertainties. So let's now finish up by looking at an example of creating a simple dashboard for your database. And really, this is the power of the database, is to be able to look at long-term trends in the data that are coming out of your lab. So when I did this, and this is just a simple example, I wanted to have a few different things in it. I wanted to create a summary of the analyses that have been conducted. Of course, this is just using this fake synthetic database, but I wanted to have some sort of summary of how many analyses have been done, and I also wanted some sort of check of the secondary standards to see how good they looked. I sketched it up in my notebook. It looks something like this. I wanted 4 different graphs. The top one would have some analyses, just the counts of the different types of analyses versus date. Then I wanted a couple of pie charts showing the relative proportions of the different analysis type and customer type. And then finally, I wanted some sort of plot of versus time of one of my secondary reference materials. The great thing about creating a dashboard like this is that it can be periodically rerun. So that, for example, you could run it at the start of each month to update this snapshot so you can see how things are trending within your lab. It does require some grouping of data. We're going to be taking the start times of each selection and we're going to summarize them into monthly data so that we can put the monthly counts of how many analyses we did. So let's look at the code for this. I just have it open in Visual Studio just because the coloring should hopefully work a little bit better for the screen. It starts off by importing NumPy, Pandas, some matplotlib packages, the date-time object, and also we're setting matplotlib to use the Qt5 ag backend. That's just so that we can create a figure that we can see. So that's all just import statements, but now let's look at how we can create a data frame from our database. Now, in the past, we've used DB specified, which returns multiple columns, but in the past, we've used select star from results, but to return all of our columns. But here I only want to return a few columns, the ones that we're actually going to use to create our dashboard. So I've said select start time, group name, group type, name, final led 206238, so we can create that chart, analysis type and work type from results. So we don't have to return all of our columns if we don't want. And I've said where group type is not equal to baseline. So we don't want to count our baseline selections. We only want to count our actual proper selections. Then just because the start time format is not necessarily strictly recognized by Pandas straight away, we want to convert this column into a date time that Pandas will recognize easily by passing it through this to_datetime function. And we're going to append the results of that to a new column called date in our data frame. So far, all pretty basic Pandas stuff. But now we're going to be using this Pandas grouper. And what we're doing is we're going to group our data by the date column and we're going to put it in frequencies of 1 month. That's what this pandas.grouper does. It will take a column that you want to group your data by, and you can actually set the frequency of it. It can be 1 month, 1 week, 1 day, 1 hour. You can check that. You can check the documentation for the options of that, and I'll put a link to the documentation for that in the notes as well. So this DG object that it's been assigned to is not really a data frame. It's more sort of a function to return the data after they're being grouped by this date column. So then using this DG object, we're going to get it to count the different values in this analysis type column, just to start off with. And there's a couple of options here. You can put normalize equals false or true. If it's true, it will show each one as what ratio it makes up of all of the counts, and you can just multiply that by 100 to get a percentage for each value type in this column. Now this DG function here will actually return a PANDAS series, but it can look a little bit strange. So I thought I would just show you what it looks like. So I'm going to do that by printing out we're going to go through the values of the index of this series, as well as the values of the series. And we're going to print both the index and the value as we go through the series. And I'm also just going to print out this little line here, and we'll come back to that in just a sec. So let's do that now in IOLITE. And just for this demonstration, I've just commented out all the rest of the code, but we'll come back to that in just a sec. So if we run this now, and I'll just make the output a little bit bigger, what we can see is that this A type, when we go through this series, you can see that it has this timestamp and an analysis type and the counts for that analysis type. And you can see that there's 3 values there for July, and there's 3 values there for August, and so on. And it has a number for geochronology, a number for hafnium isotopes, and a number for trace elements. So it can be a little bit tricky to work out what this is doing here. So I saved it as a CSV file and opened it in Excel to hopefully explain a little bit better what's going on. So when you save it in Excel, you can see that there's 3 columns. There's this date, analysis type, and another one called analysis type. But it's a little bit tricky because these first 2 are not actually columns, they're actually indices. And this is the actual column here. Then there's just one column called analysis type. And that has the counts for geochronology. So how many analyses were counted as geochronology, how many were listed as hafnium isotopes, and how many were listed as trace elements. And it has that for each month. So you can see that it's broken up into July, August, September, and so on. And so that can make it a little bit tricky because here we're dealing with indices rather than actual rows. So that's what this line here is saying. So we're actually just printing out for all indices, for all values of the first indices, for the first index, which is that date column, but just the geochronology parts of the second column. So it would print out basically this one and this one and this one here. And that's what this column means. So it says all values of this first index, but just the geochronology parts of the second index. And so you can see that's what's actually being printed out here. So it's this 70 value, it's this 787 value, and the 890 value. So they're the values that we'll actually want to plot in our time graph. So these would be the values for each month for geochronology. And we can just switch this index here around to be hafnium isotopes and trace elements to get the values we want to plot in our graph. So now that we've done that, let's look at the rest of the code. So I'll actually just run the code through just so you can see what the output looks like, and then I'll explain how it was put together. So when I run it, you can see that we have the counts, our total counts in red for all of our analyses for each month. We also have a line for the geochronology analyses, a line for the hafnium analyses, and a line for the trace elements analyses. Now this could actually be, if it was real data, it could actually tell you what values are increasing, what are decreasing. So in this case, this hypothetical data, we've had slightly less hafnium analyses in the last couple of months, and we've had slightly more trace element analyses in the last couple of months. To plot this, we need a series of X values, which are date time objects, and we need the total number of analyses for each month. Then we've got a couple of pie charts. The first one is just showing the analysis type and the work types, which is academic, government, or industry. And then finally, we're showing the values for Plezovice, and one of our secondary reference materials versus time. And unfortunately, I haven't labeled this, but that would be a good addition as well, especially what this value over here is. But that aside, let's look at how this is set up. So the first thing we'll see is that there are 3 rows in our figure, and we actually have 2 columns in our figure. It's just that the first figure here takes up both columns, and in the third row it takes up both columns as well. And you might notice that it's a slightly different style than the default matplotlib plot. That's because we're using this Seaborn ggplot approach. So let's have a look at the code. So this first line here, and I based this on a tutorial that you can see the URL for there. So we're using this plot style, the Seaborn ggplot style here, and we use that. We enable that by using this with statement. Then we create a figure, and we can put in the figure size, and then we're using this grid spec to set out how many columns we want and how many rows we want. So as I mentioned, we have 3 rows and 2 columns. Then we tell it how to break that up. So we're saying the first plot is going to take up, is going to be in the first row, and it's going to take up both columns. Then in the second row, the first pie chart that we have is just going to take up the first column. Then the second pie chart is going to take up the second column. And then finally, our fourth plot is going to take up the third row, and it's going to take up both columns as well. So when we do this, we're returning an axis object that we can then use to create the plots. So the first plot that we're going to do is we're going to do this just a typical plot that is a line plot basically. And I'm using this data grouper, and I'm looking at the analysis type column in that data grouper, and I'm going to get the count values. So it's just doing a count, and it's going to tell us how many of each type there were. How many there were in each month. I'm just using this .values function to return a numpy array just to plot the values up. That's the y values. For the x values, I'm calling the index. So I'm actually going to return the index and convert that to a numpy array. And that will give us those month end date times that we saw before, so that we know how to plot it, so that the code knows how to plot it in XY space. And I've given that a label of total, and I've just done the same thing but with this A type object that I created before. And as I said before, it's going to plot up all the different date time objects, but it's selecting just for geochronology to start off with, and we'll call that geochronology. Then we're selecting just for hafnium isotopes, then we're selecting just for trace elements. So then it's just a matter of labeling the axes and putting a legend on. For the pie charts, I'm using this normalize equal true for the value counts in the analysis type, and I'm multiplying that by 100 to give us our percentages, because that's what the pie chart wants. It wants an array of percentages. And it's also got the value counts index as the labels, so that it'll know how to label it. Same thing with the pie chart, except that this time it's using the work type. And you'll notice we're using the original data frame for this, because we're not grouping, this is not grouped by month, this is just the overall for the time that we've collected in our data frame. And finally, we have a scatter plot showing the values for Plezovice for this final lead-206 uranium-238 ratio. And I've done that by creating a data frame that only has the rows where group name equals Z Plezovice. So that's a nice and easy one to add. I should have added some axis titles and a title for the plot as well, but it doesn't matter that they're not there. I've also added an overall title for my dashboard, and you can put in whatever you like here. You could change this to be the name of your university or your company or whatever you want to do, and I've just increased the font size a little bit as well. And finally, we call figure show so that we can actually see it, and that creates this figure that we had before. I'll just run that again. And so that's how you can easily create a very simple dashboard. And if you save this dashboard.py script as a script that you can call from the database scripts button, then you can run this whenever you want, and it will update it for your most recent additions to your database. So to summarize, we've looked at how to get data from the database and how to use those data in particular calculations, whether it's creating a dashboard or if it's calculating other values and putting them back into the database. And we looked at how to append columns to the database. And ideally, you want to use this database to create insights into the long-term usage and trends in your database. And a good way to do that is via a dashboard to summarize your data. So for this week's assignment, we want you to create a dashboard of your own. You can either use your own data or synthetic data using that script that takes a session and just replicates it over time, or you can use the example database. But if you do, don't just recreate the database that I've done, because I'll provide that script for you as well. Make it your own and make it what you think would be useful to you to see. Would more secondary standard results make sense to you? Would that be useful to see if they're drifting off in one direction, like you're getting further from the truth? Obviously, in that example that I showed, there were things that should have been added, like it should have had some labels, but I could have also added the accepted value as well to see if we're consistently offset from the accepted value. The submission for this is we want to see the code that you use and along with an image of your dashboard as well. You don't have to submit the database that you use to create this, so that if you use your own data, you don't have to send that to us so that other people don't see your data before you're ready to publish it. So with that said, and also just some extra points is if you can include your lab's logo on your dashboard as well. So I really look forward to seeing what you come up with. Hopefully this is useful, and I really hope the database feature in general is useful for you. And as always, please let us know if you have any questions.